Hi, everyone. I bet you have watched the keynote by Vinos this morning on unbundling your data platform with an open data lakehouse. In this talk, Balaji and I will talk about how the fresh new Hudi 1.0 release is going to redefine what a data lakehouse can do. So first, a bit about ourselves. I'm Ethan. I'm currently a data infra engineer and tech lead at Onehouse. I'm driving key initiatives around transaction management, performance improvements, engine integrations with Spark, Flink, Presto, and Trino. I'm also a Apache Hudi PMC member and committer. Before joining Onehouse, I was a senior engineer at Uber, working on large-scale mobile networking and data problems.
Hi, my name is Balaji. I'm currently an engineer in applied intuition, where I am building a data lakehouse for ADAS and AV use cases. I'm also currently a PMC in Apache Hudi, and previously I was a senior staff engineer working in Robinhood's data lake infrastructure.
Thank you, Balaji. So for this talk, we'll start with how and why we imagine the lakehouse in Hudi 1.0. We'll talk about and dive deep into the new storage format in 1.0 and advanced indexing and the migration to Hudi 1.0 before concluding the talk. So let's first talk about why and how we imagine lakehouse in Hudi 1.0. So today, Apache Hudi is more than just a table format. It serves as a comprehensive lakehouse platform designed for data ingestion and processing. It's equipped with a range of features and services aimed at maximizing the efficiency of both writing and reading data. So at the foundation level of this platform lies the data lake storage. This is where all the data resides, stored in prevalent data formats like Parquet or Avro. These formats have been designed for efficiency and scalability, ensuring that the data is stored in a way that's both space efficient and easy to access. Upon this space, Hudi provides a transactional database layer. This is where Hudi provides the core primitives, including upserts, incremental querying, and snapshot isolation. This layer is where Hudi's true power shines, as it offers multiple services, including table services, indexes, and concurrency control with ASIC guarantees, among others. These services collectively offer significant enhancements to data and table management. Table services facilitate the handling of data at scale. Indexes speed up data retrieval operations, and concurrency control ensures the concurrency of data across multiple write operations. After data has been successfully ingested from various sources, including data streams, database, and cloud storage, and effectively managed, Hudi offers the ability to connect this processed data with popular engines like Presto, Trino, Athena, and more for different types of analytics. By facilitating these integrations, Hudi allows for efficient and advanced querying of data. Hudi is proven at a massive scale as a lakehouse platform, as you can see here of the success stories. ByteDance, TikTok, Uber, Walmart, and G all use Hudi for their mission-critical applications. Across the board, we can see Hudi powers fast and fresher data efficiently and at scale. Feel free to check out these blogs on all the use cases. Today, Hudi has a thriving community that validate the vision of the streaming data lake or lakehouse. It's almost 5 years since Hudi was incubated, and the design choices that we made back then have stood the test of time, with Hudi deployed from few hundred terabytes to exabyte scale. But revisiting those choices is important to see where the challenges are and unlock new opportunities. And now you can see on this slide that there are lots and lots of opportunities Hudi faces in these 5 years. And we've summarized the opportunities in 5 areas. And first, the deeper query engine integrations, then generalized data model for structured data, and serverless versus serverless model for serving metadata more efficiently, and support for complex, unstructured, and large blobs with indexing for machine learning and AI use cases. And last but not least, the enhanced self-management. Based on all of these opportunities, now as a community, we think it's a time to realize a more ambitious, yet definitively needed vision of providing a more generous purpose database experience on the lake. So we reimagine Hudi in Hudi 1.x as the transactional database for the lake with polyglot persistence, raising the level of abstraction and platformization even higher for Hudi lakehouses. And in fact, Hudi already provides functionalities like access method, log manager, and utilities and services that are core components in a database system. And let's look at the core components of typical database system shown on the left side diagram. There are client communication manager on the top, process manager, relational query processor, and transactional storage manager on the bottom, and shared components and utilities on the right side. Hudi 1.0 envisions the experience on a data lake or a lakehouse to be database-like by providing the same components. Hudi provides the same building blocks and interactive engines. As Hudi has deeper integration with query engines, the query optimizer and plan executor components will use Hudi's advanced indexes to do more optimization for unprecedented performance, which I'll dive deeper later in this talk. So let's dive deep into the new storage format in Hudi 1.0, which is the foundation for data and concurrency control. So let's first talk about redesigning the Hudi timeline. Hudi timeline is the core component of a Hudi table. It is an immutable event log of all transactions that have been done on the table. Typically, transaction log grows linearly with the number of commits. At times, we need to walk back and look into the archive timeline for like a long history back for time travel or understanding the history of the table. However, compared to active timeline, which are easy and fast to access, archive timeline is expensive to access in reads and writes based on the current design. So to address that challenge and issue, we resolved to the LSMM trees. So LSM trees comprise multiple tree-like structures at different levels, each of which can be further optimized for underlying storage medium. LSM trees provide fast index access to the key value pairs that hold and suitable for high-throughput workloads. So in 1.0, we have reshaped our timeline to be organized into a LSM tree. Say in this example on this slide, you have some instance in a Hudi table from T101 to T200 and so on. Storing each file per commit on this can be costly, especially on cloud storage. So with LSM tree, we will compact some of those to bigger files and push it down into the tree. The beauty of such a structure is that you can keep the top level in memory and still load the remaining levels efficiently from the disk if you need to walk back longer history. After several instances are accumulated as a batch on the active timeline, they will be flushed as a Parquet file into the LSM timeline. So in this way, we maintain fewer files on the timeline while still keeping a long history, let's say 10 years for a given table. In general, the timeline is comprised with fewer Parquet files with the LSM tree style layout. Each new operation to the timeline uses a new snapshot version as before. So another key part of making Hudi Lakehouse closer to database is the concurrency control. And it goes without saying that concurrency control and transaction management lie at the heart of it. I want to first motivate the complexity of this issue through two examples as shown in these diagrams. So in the left diagram, we have two writer processes. An ingestion writer job producing new data every few minutes, and a deletion writer job that is enforcing GDPR deletes, taking 2 hours much longer to issue deletes to the table. It's very likely for these two writers to overlap with the files on the random deletes. Now, some systems offer snapshot isolation with optimistic concurrency control, the OCC, but at the cost of aborting and retrying the other transaction. So with OCC as a consequence, the deletion job is almost guaranteed to starve and fail to commit each time due to its longer duration. And overall, mixing long-running transactions leads to disappointment instead of optimism, since the longer the transactions, the higher the probability they will overlap. So now let's look at the right diagram. So Hudi already provides the option of running the table services in async fashion, where most of the heavy lifting, for example, actually rewriting the data by convection, is done asynchronously, eliminating any repeated waits for retries whatsoever. We are also optimizing the table using, for example, clustering techniques. So a single writer would consume both the regular updates and GDPR deletes and serialize them into a log. So by taking these kind of insights of async table services, let's look at how Hudi 1.0 solve the high concurrency with non-blocking concurrency control for concurrent writers. So we introduced like the conflict resolution at read time with the new completion time notion. So this completion time complements the current instant time or start time so that each transaction can be represented as a time span on the timeline instead of like a single time point. So in this way, we make sure that both writers can write to the same file group. Even if they have conflicts, they can write logs or updates into different files and then commit successfully. So in this way, there's no blocking at write time. That's how non-blocking word is derived. And we resolve the concurrency or conflicts at reader side by using completion time ordering. So in this way, we are able to resolve conflicts without actually retrying or failing the concurrent writer if there are conflicts. To make sure this completion time is ordered and guarantees the serializability, we introduce the spanner's true time like global monotonically increasing timestamp for the AC guarantees. So this is how Hudi improves the concurrency. So and this especially benefits the high throughput streaming jobs. Besides the timeline and non-blocking concurrency control, we also introduce new format changes and efficient updates and deletes. So as you know, Hudi has the merge and read table type, which is battle proven for fast upsert, and it supports key-based merging. So in Hudi 1.0, we introduced the first class support for efficient updates and deletes using positional merging. This means that for merging base and log files, we use positions instead of record keys, which can do position skipping and also improve the performance by more than 20% when there are a lot of updates. We also natively support partial update with the log file in MR table. We only encode the change columns among like a white table. Let's say if the data is only updated for a few columns or tens of columns among a white table with thousands of columns, we only encode the change data of those tens of columns. In this way, we reduce the storage bytes by 99% for such white tables and improve the write and query performance by 6x. This is natively supported now with MR table in Hudi. To further make engine integration easier with all these optimizations, we introduced a new file group reader. This new file group reader API unifies all the merging logic in Hudi, so makes engine to worry less about how to implement the merging logic correctly. Next, let me dive deep into how Hudi 1.0 unlocks the unprecedented query performance with advanced indexing. So index is widely employed in database systems, as you all know, such as relation DBMS and data warehouses to locate information quickly. And this is similar to how an index page at the end of a book helps you locate information. In data systems, such indexes are used to reduce I/O costs and commonly used to improve query performance. Hudi uses indexes to locate record efficiently and do fast upserts. And as you can see in the diagram, without index to apply updates and deletes, each data file has to be merged against all the updates and deletes for the table. However, with index, Hudi merges each file with the updates and deletes only for that file. So as you can already imagine, this significantly reduces the I/O for merging data. Hudi supports different types of index such as Bloom filters index, H-based index, and record level index. To efficiently manage and fetch index metadata, Hudi introduces the multimodal index subsystem, and it is used on both the write path for efficient upserts as well as the read path for faster queries. If we look at what happens behind the scenes when executing the query, the first step involves fetching the metadata, followed by query planning, applying some optimizations, and then eventually reading the data before serving them. So fetching the metadata is key to improving your query performance. In Hudi, the multimodal index is structured as a metadata table, an internal Hudi table with partition supporting different types of indexes. This includes file listing, column stats, Bloom filters, record level index, and the new functional index and secondary index in Hudi 1.0, which I'll cover later in the talk. So all of these indexes can be built asynchronously without blocking injection. Next, let me talk about the new indexes introduced in Hudi 1.x releases. The functional index enables user to create indexes on functions or expressions. And on the high level, the concept of functional index is simple. Just like how you would create an index column, functional index allows you to create an index on a function of a column. But the efficacy of functional index goes beyond what a simple index can do. So let's consider a case where a stream of events from microservices are ingested into a raw event table. Each event log contains TS, a timestamp column, and associated organization ID, the org ID column. Most queries on the table are organization specific and fetch logs for a particular time range. So a user may attempt to physically partition the data by both org ID and date of timestamp to just skip data that are irrelevant. So if there are 1,000 organization ID and 1 year of data, this easily translates into more than 300,000 partitions for the table. And in most cases, you can imagine that the data can be highly skewed based on organizations, with most organizations having less data and a handful of organizations having majority of data. So that there can be many small data files. In such a case, a user may want to evolve partitioning by using org ID only without rewriting existing data, resulting in physical layout of data like below. So for this example, even when the mix of old and new partitioning scheme, we should be able to effectively skip data based on the range of date string for each file when the functional index is created on the date of TS. So this happens regardless of how the files are stored on their different physical partition paths in the table. And as you can already see that it is profound that functional index absorb the partitioning into indexes, and there's no need in this case to hide and evolve partitions. Hudi 1.x also introduces the secondary index for non-primary key fields to improve query performance. The secondary index provides similar database-like experience for efficiently locating records given predicates on the non-primary key fields. And as you can see on this slide, Hudi manages the secondary index on non-primary key fields by tracking the secondary key to primary key mapping. And user is able to first create a secondary index in SQL as shown on this slide. Then when querying data, the secondary index and record index together are used to realize data skipping, achieving fewer data scan for point lookups on non-primary key fields. And as usual, the secondary index is managed by the Hudi multimodal indexing subsystem, which is automatically updated and maintained. So let's talk about these newly emerged vector and large language model use cases and how it's related to Lakehouse. So as large language model or LLM applications are on the rise, a lot of focus has been on operational or online databases that have added vector search capabilities or even specialized vector databases like Chroma, Python, etc. They offer similar capabilities of searching the vectors on a traditional database. So the data lakehouse architecture has already proven scalability and cost effectiveness advantages compared to storing all data for analysis and processing in shared nothing database architectures or data warehouses. And we believe that extending data lakehouse storage and query engines with vector search capabilities can unlock best of both worlds with exciting outcomes. So we are introducing vector index to support vector search capabilities in future Hudi 1.x release. First, the vector embeddings are stored in the data lakehouse. So the lakehouse becomes the source of truth store for all embeddings, while moving portion of it into online vector databases for serving user-facing applications. This approach overcomes the pain of storing and scaling large amounts of embeddings in an online database forever, reducing cost, while also allowing production database to be more efficient and easier to operate. So storing embedding in the lakehouse unlocks the ability to run large vector searches in an offline manner to either serve internal business use cases or just understand the behavior of LLM applications. This is similar to using data lake for exploratory data science while keeping a separate online database for powering user-facing applications. To support fast vector searches on Hudi tables, storing embeddings directly, we are designing and implementing a new vector index that is maintained by the same Hudi multi-model index subsystem. So the user creates a vector index on the column of the Hudi table, and Hudi automatically updates the vector index based on inserts, updates, and deletes. And when doing vector search on Hudi table through SQL, the vector index is used to unlock efficient lookups. And given much of the embedding data is updated from the data pipelines, every so often we can provide reasonably fast serving vector queries, let's say like 80% speed at 80% lower cost, by either extending the lakehouse storage using Hudi's new vector index, or adding a caching tier or tier storage integration into existing online vector databases. So this vector index is still work in progress, will be released in future 1.x releases. So next, I'll hand off to Balaji to talk about the migration to Hudi 1.0.
Yeah, thanks, Ethan. So now that we have looked at these awesome new features of Hudi 1.0, let's look at how to deploy the new version to your lakehouse. Next slide, please. Okay, so let's consider the benefits of migrating to Hudi 1.0 in the first place. So with Hudi 1.0, we gain access to latest Hudi features on our existing tables. Features such as non-blocking concurrency control and functional indexing can be leveraged on existing datasets. So other important benefit is like better query performance in existing tables. The optimizations in Hudi 1.0 are generally geared towards like enhancing read and write operations, leading to faster insights and more efficient data handling. So importantly, migrating to Hudi 1.0 using paved path allows us to upgrade without the hassle of rewriting the entire table. This not only saves operational downtime and workload, but also avoids the cost of such rewrites. Finally, if there are new use cases that would benefit by using Hudi 1.0, by moving the entire lakehouse to Hudi 1.0, we can avoid the complexity of maintaining multiple Hudi versions. This also has a nice side effect of making existing workflows more efficient and systems generally easier to manage for the operators. In summary, like migrating to Hudi 1.0 is like a strategic move that has long-term benefits of enhancing your data operations and improving your overall lakehouse performance. Next slide, please. Yeah. So when it comes to migration challenges, so essentially like the storage format for Hudi 1.0 is not compatible with the prior versions. For example, the Delta log file naming have been modified to support non-blocking concurrency control. Timeline file names also now includes the completion time of the actions that have happened. So this basically means as part of 1.0 rollout, an upgrade process needs to run on existing tables. Being a lakehouse platform, Hudi finds itself as a key part of several components that make up the lakehouse. There is basically processing engine integration such as Spark and Flink, and also there is all these table services that are needed for running compaction and clustering through Spark. And there are also like typical query engine clusters such as Presto, Trino, which also integrates with Hudi. So when we say upgrading the Hudi, generally means that basically upgrading Hudi across all these different components. And we are not only changing the library here, but also the storage format. So therefore, it requires careful planning. We need to consider like typical deployment model, the jobs and services that uses Hudi here. So general strategy like basically making Hudi 1.0 reader backwards compatible and upgrading the reader first before the writer does not usually work because the typical ETL jobs play both the role of reading and writing within the same application. So next slide, please. So therefore, I've adopted a strategy where to support this migration, we are adding basically a new support in Hudi 1.0 to read and write in the previous release storage formats. So in Hudi, there's a concept of table version to identify and track storage format changes. So this is set typically during the table creation time or during any upgrade or downgrade process. It is also updated. You can generally see this config value in the value in the Hudi.properties file. With 1.0, so Hudi introduces a new right side configuration, which allows you to override the table version on the writer side. So for context, basically an existing table written using the previous release, which is the Hudi 0.15 release version, will have the table version set as 6. In 1.0, the table version is 8. And so with 1.0, when a writer table version is set at 6, no upgrade happens and the writer continues to write in the previous storage format. So this basically means that the existing Hudi 0.15 readers will read the table written by the 1.0 writers without any side effects. And in 1.2, the readers basically will use the table version defined in the Hudi properties file to dynamically adapt to 0.15 or 1.0 storage formats. So now, basically, if you want to do an upgrade, the writer side will basically set this new table table version config on the writer side to 8 to basically force the upgrade to 1.0. This basically means that the storage format of the data gets upgraded to 1.0 version and the basically unlocking all the 1.0 features on the table. Next slide, please. So, so generally, like with that, basically, you can think of upgrading your lakehouse in basically two different phases. In the first phase, we deploy the library and services to the entire lakehouse stack, but making sure that the writer is preserving the 0.15 storage format. In the second phase, we can enable the 1.0 storage format at table level granularity to force the table upgrade at our own cadence. Next slide, please. Oh, that's it about the migration. So here are the links to the technical specifications for 1.0. We also have a beta version to try out Hudi 1.0. It's available in Maven. And next slide, please. Yeah, so finally, Hudi is community driven and we love new people to come and join us and build new features. So here are the resources and there's a QR code to join the Hudi Slack to ask questions and generally discuss about Hudi with the community. Yeah, thanks.
Thank you, everyone. Please enjoy the other talks at Open Source Data Summit. Bye.